All right, so in this part of the module, we're going to talk about the main reason why we not only have covalent and ionic bonds in terms of different types of bonding, but even in the realm of covalent bonding itself, electrons can be shared in different ways. And the different types of bondings that we come across are based on differences in what is known as electronegativity. And along with that, especially as it pertains to our covalent bonds that we'll classify as being polar covalent, we're going to talk a little bit about bond polarity as well. Okay, so let's start with a little bit about electronegativity first. In terms of a definition, electronegativity is the ability of an atom to attract electrons towards itself. Now, as we'll talk about, some elements, their atoms have a great ability to do this. Other elements, their atoms have a very poor ability to do this. To sort of give it, to define the electronegativity of an atom, numerical values are usually assigned. The lower the number, the lower the electronegativity, the higher the number, the higher electronegativity. One of the most used scales that is used is what is known as the Pauling scale. And in reality, I really have never used any other type of scale to sort of assign values to electronegativity. In reality, it's really always been based on the Pauling scale. On the Pauling scale, you have electronegativity values that are less than 1 for some elements. We'll talk about that. And then up to 4.0, the highest electronegative element, which, as we see on the slide here, we'll talk about, is fluorine. Now, it turns out that the way the elements are positioned in the periodic table, their closeness to each other, their positioning in the periodic table, does reflect some ideas about electronegativity. And essentially, when you have properties of elements that can be described by positioning in the periodic table, either elements in the same period, so to speak, or elements in the same group, so to speak, you have what are known as periodic trends. Electronegativity fits into that category because we can make predictions based on electronegativity, based on where the elements are situated in the periodic table. And there are some trends that you find, not only within a period, but within a group as well. Other properties where you would have these periodic trends would be something like atomic radius, ionization energy, things that we're not going to talk about in this course. Now, usually electronegativity increases going from left to right across a period on the periodic table. You know, there could be exceptions to this, and I believe there are, but the general trend that you see across a period in the periodic table going from left to right is that electronegativity usually increases. On the other hand, electronegativity usually decreases in a group in the periodic table, going from top to bottom. So essentially, the two periodic trends for electronegativity is that across a period from left to right, electronegativity usually increases, and then in a group, as you go from top to bottom, electronegativity usually decreases. Now, it turns out that nonmetals tend to have high electronegativity values. So let's sort of think about the rationale for that. If you think about what nonmetals have done so far in chemical bonding, we've seen them share valence electrons, but we've also seen them do what? We've also seen them gain valence electrons. So if you think about the idea of being able to gain valence electrons, that really speaks to having a high attraction for electrons. Because if you're going to want to gain electrons, you're going to want electrons to be attracted to you. So it sort of makes sense in my mind why nonmetals should have high electronegativities. Because yes, they share, but we've also seen them gain. And if you want to gain, you should have a high attraction for those electrons. As I mentioned, fluorine is the element in the periodic table that has the highest electronegativity. Now, on the other hand, metals tend to have low electronegativity values. And if you think about that in terms of metals and chemical bond formation, what is the only thing we've seen metals do? The only thing we've seen metals do is lose their valence electrons. So if metals essentially always lose their valence electrons in bond formation, does that speak to them having a high attraction for electrons? And the answer is no, because they're basically giving the electrons up. they're essentially telling the electrons to stay away. Now, in terms of the periodic table, there's one element that's really out of place in terms of electronegativity and its position in the periodic table. And what element is that? That element is hydrogen. Because as we know, hydrogen is not a metal, even though it's usually a part of group 1A. Hydrogen is not a metal. Hydrogen is a non-metal. So in terms of electronegativity, it would belong with the rest of the non-metals. Specifically, it belongs right next to carbon. It actually, in theory, should really fall right in between boron and carbon. So essentially, it belongs next to carbon. Okay. Hydrogen on the Pauling scale has an electronegativity of 2.1. Carbon on the Pauling scale has an electronegativity of 2.5. But the fact that in terms of electronegativity, they should be next to each other speaks to their similarity in terms of electronegativity, because when elements are close to each other in the periodic table, they should have similar electronegativity values. Okay. So you don't have to memorize the electronegativity values, okay? You know, if I was to give you questions about electronegativity, I would give you some of these values here. These values, of course, are reflective of the Pauling scale. They also reflect the trends. Usually speaking, from left to right, across a period, electronegativity increases. And then if you go in a group from top to bottom, electronegativity usually decreases. But again, if you notice in looking at some of the groups and such, you know, that's not always the case, okay? So there's some exceptions to, you know, the general trends that you see, but, you know, they're pretty decent to make predictors, especially, you know, as you go across a period with a metal to a non-metal, or in a group if you're at the top versus the very bottom. You know, you could probably make very accurate predictions. The other thing to mention is that if you look at group 18 or 8A, those elements, the noble gases, don't have any electronegativity. And if you think about it, you know, noble gases already have their octet rules satisfied. So as we've seen, they don't really participate in chemical bond formation. So they don't want to gain electrons. They don't want to lose electrons. They don't really want to be involved in any attraction for electrons. And that's why essentially your noble gases don't have any electronegativity values associated with them. Okay. So as I mentioned a little bit earlier, there are actually two types of covalent bonds that you come across. The first type of covalent bond that you come across are what are known as nonpolar covalent bonds. Just like any covalent bond, you would find a nonpolar covalent bond between two nonmetals. In a nonpolar covalent bond, you either have an equal or an almost equal sharing of electrons. And the result of that is that in a nonpolar covalent bond, the atoms are truly neutral. There's no charge at all associated with the atoms in a nonpolar covalent bond. Because if you have an equal sharing of electrons, essentially the electronegativity difference between the two atoms would be zero. And you see that on the bottom here in the case of a nitrogen bond, because here the electronegativity difference is zero. So in that particular case, the electron sharing would be equal between the two atoms. You know, we think about where the electron density, the concentration of electrons in that bond would be found, it would really sort of be found right in the middle. However, even if the electronegativity, even if you have an electronegativity difference, if that electronegativity difference is small, and basically when we say small, we're talking about less than 0.5 difference. Basically, the attraction that one of the atoms will have over the other is not really large enough to pull the electrons towards that atom more than the other. So essentially, the electron density would really be concentrated right in the middle. Some examples of that would be a bond between chlorine and bromine, where the electronegativity difference is 0.2, 50-50 sharing of electrons. The atoms are technically neutral. HS, where the electronegativity difference is 0.3, 50-50 sharing of electrons, basically, the atoms are technically neutral. Just also want to point out, carbon to hydrogen, the difference in electronegativity is 0.4. As I mentioned earlier, carbon 2.5, hydrogen 2.1. So what does that mean about a carbon to hydrogen bond? It means that is not the carbon to hydrogen bond is nonpolar covalent. And for a carbon to hydrogen bond, the carbon and the hydrogen are technically neutral. And that's an important one going forward, especially if you're going to go on and take organic chemistry after this. The other important one in a sense would be a carbon to carbon bond. You know, essentially, if you have any of the two same elements bonding to each other, the electronegativity difference is always going to be 0. And again, we're talking about non-metal elements. The electronegativity difference is always going to be 0. So you're going to have a nonpolar covalent bond. Right? So any carbon to carbon bond essentially would be nonpolar covalent. Biggest thing to remember, equal sharing of electrons. The atoms are technically neutral. Okay. The other type of covalent bond that you come across is a polar covalent bond. Now, again, since it's covalent, it's going to involve non-metal atoms. But here, the electronegativity difference is large enough that one of the atoms is going to pull the electrons towards itself. So that the electron density, the concentration of the electrons in that bond, is not centered in the middle, or not centered sort of right directly in between, in the middle of the two atoms. It's going to be shifted more towards one atom than the other. And because of that, you have what is known as an unequal sharing of electrons. The electrons are being shared, but they're shifted towards one atom more than the other. So one atom is going to feel, we'll talk about this, one atom is going to feel those electrons more than the other. Because of that, one of the things about the atoms in a polar covalent bond is that the atoms are not technically neutral. And we're going to talk in a few moments about what type of charges the atoms have in a polar covalent bond. But the biggest thing to remember here is that the atoms are not technically neutral. In terms of the electronegativity difference, for a polar covalent bond, usually it's about 0.5 to about 1.7. So if you have nonmetals where the electronegativity difference is 0.5 to about 1.7, you have a polar covalent bond. And here are some examples of that. OCl, the difference is 0.5. ClC, the difference is 0.5. OS, the difference is 1.0. So these would be all polar covalent bonds. All right. So as we saw on the last slide, in a polar covalent bond, the atoms are not technically neutral. One of the classic examples of a polar covalent bond that wasn't mentioned on the last slide is OH. In OH, oxygen is the more electronegative element. Hydrogen is the less electronegative element. And again, you would know that just by looking at the electronegativity values for these substances. Let's see if we can write this again. Okay, so oxygen would be the more electronegative element, and hydrogen would be the less electronegative element. So, and the difference, I think, is oxygen 3.5, hydrogen 2.1. So I think the difference is right around 1.4. So in a polar covalent bond, the electrons in the bond are shifted towards the more electronegative element, because that element has more of an attraction for the electrons in that bond. So if it has a higher attraction for the electrons are going to be shifted towards it. Now, what type of charge develops on that atom? Well, you think about the charges of electrons. And what charges do electrons have? Electrons have a negative charge. So if you're shifting electrons towards the more electronegative element, what charge is sort of that element feeling? Is it feeling more of a positive environment, or is it feeling more of a negative environment? Well, if the electrons are being shifted towards the more electronegative element, that element is feeling a more negative environment. We term that as a partial negative charge, given by the symbol delta minus. Why only partial? Because the electrons are not gained. That would give us an ion with -1 or a -2 or a -3 charge. But the electrons here are shifted towards, and that's why the charge is partial. So in our example of OH, with oxygen being the more electronegative element, the oxygen would have a partial negative charge. Now, on the other hand, the electrons in a polar covalent bond are shifted away from the less electronegative element. Right? If the other element has more of an attraction for the electrons, well, then they're being shifted away from the less electronegative element. So if the electrons in the bond are being shifted away from the less electronegative element, what charge is the less electronegative element feeling? Is it feeling more of a positive charge, or is it feeling more of a negative charge? Well, if the electrons are being shifted away from it, it's feeling more of a positive charge. The name given to that charge is what is known as a partial positive charge, given by the symbol delta plus. Again, why partial? Because the electrons are not being lost from the less electronegative element, they're being shifted away from. So that element feels more of a positive environment. So going back to our example of OH, the hydrogen would have a partial positive charge. Other ones that I think you should be familiar with coming out of the course, NH, where the nitrogen is partial negative and the hydrogen is partial positive. C double bond O, where the carbon is partial positive and the oxygen is partial negative. You can also have hydrogen to halogen. You could have carbon to halogen, where for both the hydrogen and the carbon would essentially have partial positive charges, and the halogen would have a partial negative charge. Okay. Finally, we get to ionic bonds. As we know, ionic bonds occur between metals and nonmetals. And ionic bonds are the force of attraction between ions of opposite charge that result from electron transfer, the metal losing its valence electrons, which are gained by the nonmetal. Now, why does electron transfer take place? Electron transfer takes place because the electronegativity difference between a nonmetal and a metal is so large that the nonmetal says, you know what? I'm not going to share these electrons at all. I have so much more of an attraction for them that I'm just going to take them. And the metal says, okay, take them. I don't want them. I don't have much of an attraction for them. Take them. And now the electrons are no longer shared. Now the electrons are transferred. And essentially, between metals and nonmetals, you essentially have electronegativity differences of 1.8 or more. So each of these bonds here, even though they draw dashes, which I don't know if I really agree with, but each of these bonds here would be ionic. even though we know metal, non-metal should be ionic, the electronegativity difference being 1.8 or larger really speaks to the fact that these are ionic bonds. And then on the last slide here, they just give you some examples about some different bonds, picking the type of bond it is, whether it's nonpolar covalent, polar covalent, or ionic, and the reason behind it. And basically, it fits into the discussion that we